Sorting algorithms are everywhere, whether it's cleaning up your desktop, asking for a job interview, or just looking cool. Sorting algorithms are all around us, and this is why I'm going to take you through 4 sorting algorithms that I think you will absolutely love. Let's start. A thing called big O notation, and big O notation is just any like other functions. So functions are represented like this. I'm sure you're familiar with it. There's functions like all of these you can see on the screen right now, but in our case we're going to call our function w of x, which stands for work. Now on the x-axis we're going to have the n number of items we're trying to sort using our sorting algorithms, and on the y-axis we're going to have the time taken for the sorting algorithm to sort n items. So big O notation is represented as this, and big O brackets n, and that n is actually the function. So this is what w of x is equal to. So if we have big O of n squared, that means our function w of x is equal to x squared. And I'm sure you get the gist. So let's start off with our first sorting algorithm. Our first sorting algorithm is bogo sort. Now bogo sort is famous for being really inefficient. So you have got an array of numbers, and as you can see they are not sorted. My cursor here is pretty big and I'm going to use that as the pointer. I'm going to start at the first number, and what bogo sort does is it first just tests if the list is sorted or not, which it compares, it starts at the first index, which is right here, and it compares it to the one before it. If it is less, then you can say that that part is sorted, and you keep going until it's sorted. So that's 6, 10 is obviously not less than 6, so it is not sorted. Then it just keeps to randomly shuffling the list until it's sorted like this. So as you can see, it is sorted. And bogo sort has a big O function of big O of n factorial, which is really super inefficient. So please do not use bogo sort, but we're going to move on to some pretty cool sorting algorithms later in the video. Which in Python I've actually writ to do the bogo sort algorithms. So the first section here is defining the bogo sort function. As you can see, it iterates through all of the elements to see if the list is sorted. And here's our array. We're going to sort. Obviously this is not sorted, and let's see how many attempts this takes. So I'm going to run, and it's sorted, and it took 12 attempts to do it. So if I add one more list item, say 5, I'm going to run this again. It took 188 attempts to sort the algorithm, sort the list, which is really inefficient. Our next sorting algorithm is called bubble sort. So let's get into that. And it's not as inefficient as bogo sort, but it is still not the best sorting algorithm. So it starts at the first index, and it compares the index before it, right here. If the index it's currently on is less than the index before it, it switches these two. So it switches these like this. And then that's the first iteration. So now we go on to this one, which is a 3, and it is less than this index here. So we switch these two, like this. And it keeps repeating that until the list is sorted. Now bubble sort has a big O function of big O of n squared, which is a quadratic or parabola runtime. It's still not the best sorting algorithm, but it does do the job. I've wrote for the bubble sort algorithm. So, of course, we define our function to check if the list is sorted or not. How we have a oh my god. We have our variables here, and we have this flag to indicate if any swaps happen to go past true. The main thing right here is it just compares the previous index to it. If it is greater, it swaps and etc. blah 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 blah. So if we try this out for a 5-item list, it took 3 iterations, which is a pretty good runtime for the bubble sort. Our next sorting algorithm is one of my favorites, is called insertion sort, and it goes like this. We have our list of numbers in the array like this. I've got to fix that up. And we have a temporary storage right here, which just holds a single number temporarily. It's like the computer RAM. It just holds a number for a very short time. Alright, let's begin. We first start at the first index with our pointer, and we store that in the temporary storage, as so. Next, we compare all the items to the left of it. We compare all the items to the left of it. If those items are greater, we shift them over like that. But in this case, 1 is not greater than 3, so we just return this back into that value. Next, we go to the second index, which is 6. We put it here. 3 is not greater. Sorry, 3 is less than it, not greater, and 1 is not greater as well. So we just put it back here. We go to 10 now. Obviously, these ones right here are not greater than 10, so it just returns it. 8, however, we can put this here. And 10 is greater, so we shift 10 up. 6 is not greater, 3 is not greater, and 1 is not greater, so we just return the value. We keep repeating this until the list is sorted, as so. Now, insertion sort has a pretty good runtime. It has the best case runtime of insertion sort is big O of n, which is a pretty good runtime in my opinion. And this is the second last sorting algorithm, and the next one is going to be really good, so stay tuned. Code for insertion sort. I'm not going to go into the high details of how it works, but we just iterate through the indexes here and shift them over blah 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 blah. So if I have here a 1, 2, 3, 4, 5, 6, 7, 8 item list, I think. I'm going to bring that up, and it takes 7 iterations to go through that list, which is a pretty good runtime. Let's add another one right there. And we get 10 iterations for that list, which is a pretty good one. Our next sorting algorithm is going to be great. This next sorting algorithm is called timsort, and it's what Python and JavaScript uses in their built-in sort functions. So the first thing we're going to do is going to divide our array into runs. Now a run is a subset or subarray of 4 items. So we're going to divide them like this, and we're going to sort each run using insertion sort. Split into runs, right, like that, and sort them using insertion sort, like that. And we're also going to bring in a temporary thing, and we're going to merge them using merge sort. So we're going to take the first one of each list, and then compare it. This one is bigger, so we mark this as the biggest one and we put that down here. And then we compare this to it. Okay, that makes it bigger. So we put this here. And 2 becomes the largest one. And then we compare one from here. 2, it is the same. So we're going to just keep that there. And then we're going to take this one. Here is the newest, biggest, because 9 is greater than 2. We're going to put this back into our array. This becomes our new biggest one. We're going to compare this one here to it. It isn't bigger, so we just put it here. 16 is bigger than that, so this becomes our new biggest. Is our new biggest. 7 is our smallest, so we actually need to compare it to 9. If it's less, we just need to swap it like this. And then finally we only have 16 left, which goes in the N1. And our array is sorted. This sorting algorithm is one of my favorites. It's just so beautiful as merging and dividing. And that is going to be our last sorting algorithm for this video.